everyone, and welcome to the second week in our module about the stratosphere and the ozone layer. This is week 5. I hope you're enjoying the module so far. This is really the fun lecture, at least for me. I enjoy talking about the ozone layer and all the air pollution involved in what's going on. So now that you have the fundamental chemistry understanding, I'm going to go ahead and tell you about everything about the stratosphere and not everything, but I'll tell you about the issues with the stratosphere now. Okay, let's get started. So here is our diagram about the atmosphere that you remember from the tropospheric chapter on air pollution. So as you remember, when you're at the surface of the Earth, and this is right here at the bottom, right? And again, you have the Celsius temperature. Here is the 0, and if you go to the left, it's going down in temperature, and if you go to the right of that 0, it's going up. The y-axis is going up in altitude. So when you're in the troposphere, as you go up in altitude, the temperature starts to drop. It gets colder and colder and colder until you hit this point called the tropopause. When you hit the tropopause, you have a temperature inversion, where as you go up in altitude, your temperature actually starts to increase until you get to the point of the stratopause. This region between the stratopause and the tropopause is the stratosphere. The stratosphere is actually like where your planes fly, or the jets, where the jets actually fly up in the lower regions of the stratosphere. And the stratosphere is also famous for the ozone layer. And this ozone layer is actually responsible for this heating process of how the area actually, as you go up in altitude, it increases in temperature. And that is actually due to this ozone layer absorbing heat from the sun. The other thing interesting about the stratosphere is that it actually does not really have what we call weather, because normally in the troposphere, heat rises up to the cooler regions. And then once it hits the tropopause, where the temperature starts to go back to hot, the air sinks back down. So you have this vertical motion of air as well as horizontal motion of air. And so this is what causes really a lot of our weather down by the surface of the Earth. On the stratosphere, since it gets hotter as you go up, the air really doesn't rise. And what happens, you just get a horizontal motion of air. The stratosphere actually has a similar composition to the troposphere, the same sort of components of oxygen, nitrogen, argon. The main difference is the water vapor is about 1,000 times less, and the ozone is 1,000 times greater. About 24% of the stratospheric composition is ozone. If you look at the ozone, and then on this graph, you can see the ozone concentration on the x-axis increases as you move to the right, and the y-axis is our altitude. So from this green line down to the bottom is our troposphere. Notice that we have ozone, this red line here, means that you have higher ozone down here towards the surface of the Earth. And again, remember from our tropospheric air pollution chapter, the ozone near the Earth, the surface of the Earth, is a pollution. It's caused from burning fossil fuel. It's actually a toxin down close to the Earth. And as you move up in altitude, actually the ozone decreases, the concentration. But as you get beyond the troposphere, all of a sudden your ozone increases in concentration dramatically. This is your stratospheric area. And the ozone layer in the stratosphere is natural. It's been there since we've had life on Earth. We've had an ozone layer. So it's actually essential for our life here on Earth. And what we refer to as the ozone layer is basically this region here in the stratosphere with maximum ozone concentrations. Now, why is the ozone layer so important? What is this focus? Why do we spend a whole chapter talking about an ozone layer and spend all this time learning a background about chemistry and how to bond atoms and Lewis structures? Why is it so important? Ozone in the stratosphere basically protects life on the surface of the Earth from harmful UV radiation from the sun. If you look at this diagram here, these little squiggly lines That's the sunlight coming down from the sky, and it hits these ozone, these yellow dots. You see the molecule with 3 yellow dots? These are your ozone molecules. And so what happens, that sunlight, the UV radiation, hits the ozone, and it absorbs a lot of that harmful radiation, and so it never gets down to Earth. These molecules with the 2 red dots are actually oxygen. You can see that the UV radiation just goes right past the oxygen and hits the Earth. And this is what normally a model of how our Earth should look. But if for some reason this ozone layer we have here is depleted or lowered in concentration, we would have, for example, more oxygen molecules, and you'd have more UV radiation hitting the surface of the Earth. And I'm going to tell you a little bit about the nature of light. And UV radiation is actually a form of light. And so the way to think about light is kind of like the ocean. And that's kind of how the light moves, like a wave. And we actually refer to this area between 2 peaks. See how there's 2 peaks of the waves? This is a wavelength. It's the length of that wave. And we represent that wavelength with lambda, this Greek letter. And it's typically given in the units of nanometers. Frequency is another term we use a lot with light, and you can use the same thing with the ocean. If you have like a day where there's like all of a sudden the waves are coming fast, that means you have a higher frequency. So if you look at the first wavelength in the red, you can see how they're separated. The wavelength is separated further apart, and within that same time frame, okay, you can see you have more wavelengths in the blue line, or the purplish blue line. So that means you just have more wavelengths in a certain amount of time. And notice that the frequency is given in n, and it's defined as the number of waves passing a fixed point in 1 second. So again, time frame is the important factor here for frequency, just how often it's happening in a certain amount of time. The units you typically see is waves per second, or 1 over second, or second to the -1, which is the same thing as 1 over second, or it's also given in hertz, which also just means 1 over second. So the wavelength and the frequency are often related, and you can see that here with this equation, where C equals L is just another way to say lambda. Lambda times n, that's your frequency, and C is this magic number. It equals 3 times 10 to the 8 meters per second. That is the speed of light. The speed of light, which is incredibly fast. So you're looking at the nature of light. In the end, ultimately, you can get this equation about the speed of light, which is related to how long the wavelength is and how often it occurs. So the electromagnetic spectrum is basically light, all right? And we can actually pull apart the different portions of the light and view them in a prism. All this red to blue is a visible portion of light that we can see, but there's areas of the spectrum we can't see. Bugs can see them. You know, a lot of bees can see colors beyond ultraviolet or violet. So again, this is our visible light region. You have red all the way to violet. Notice the wavelength is longer for red and shorter for violet in the nanometers. So this is our wavelength. You can see it also in the wavelength here. Here is a longer wavelength coming from the red or the low energy region all the way to the higher energy region. And we say it's a higher energy region because notice that the wavelengths do get shorter over here, but the frequency is higher. And so energy actually is related to this constant called Planck's constant. Don't worry about where it came from. Just know it's a constant. You can look it up in the textbook, but it's just 6.63 times 10 to the -34 joules per times second. And that constant is times by n. Okay, guys, what was n again? Remember n, let me show you. Frequency. Frequency is n. So that's how often the wavelengths are occurring in a time frame of a second. So the more frequent, right, and that means there's shorter wavelengths, the more energy. Okay, and that's important for us. These wavelengths that are coming down in the ultraviolet region, they're beyond the violet region that we can see. This is your ultraviolet radiation. That's just beyond the visible region. It has a higher energy. And that is actually why it can negatively impact us, because it has a higher energy that's hitting us, and the higher energy can actually do damage to our cells. Notice that there's a broad range here for the ultraviolet or UV radiation. There's a range. So let's talk about the different types. So when you're in a longer wavelength region of the UV radiation, that's UVA. The next one would be a little bit shorter wavelength, would be UVB. And then you have the UVCs, which you start getting more frequent, higher energy wavelengths. So typically what happens, the ozone layer will actually absorb about 100% of these dangerously high energy UVC wavelengths. The UVC are most damaging, but they can cause cancers and all kinds of mutations, but they're pretty much blocked by the ozone layer. UVB, only 5% usually get through into Earth, so 95% are absorbed. These are not as damaging as UVC, but they still are damaging. They cause skin cancer, cataracts, sunburns. And UVA, most of it actually gets down to Earth. So only 5% here, 5% is blocked in the UV layer. But this is the lowest energy, right? Has the longest wavelength, lowest frequency. So this type of radiation actually is the least damaging. So let me show you the Lewis structure of ozone. So notice that there's the three oxygens. And since it has a double bond on these two oxygens, you can actually draw another structure on the other two oxygens. So this would be your resonance structures. And since they're resonance structure, that means that these ozone bonds are not really, that means that the bonds are somewhere in between a double and a single, right? It's not really either of these structures. All this picture indicates is that the bond is between a double and a single bond. It's not the same. So just so you know some background, bond length, your single bond has the longest bond length. Okay, and that's about 147 picometers. And a double is the next one, and that's about 121 picometers. So it's a little bit shorter. And a triple bond would be the shortest bond. And since again, this is a resonance structure, it's somewhere between double and single, you would expect that actually the bond length here is 128 picometers. So it's not quite double, it's not quite single. So to show you what that would look like, a single bond length would be here, and then you would have ozone would be next, then you'd have double, then you'd have triple. Now, if you have a longer bond, they're weaker. They're easier to break. Just like if you build like a stack of blocks, and the biggest stack of blocks is easier to knock over than a short stack of blocks. So it's the kind of same idea as the longer bonds are weaker and shorter bonds are stronger. Triple would be the strongest bond, double would be the next strongest, ozone would be next, and single would be the weakest. So that would mean for you that an oxygen, which only has a double bond, has a stronger bond strength. And ozone is longer, so it would have a weaker bond. So photons at wavelengths of 280 to 320 nanometers, that's your UVCs, are just strong enough to break ozone bonds. Okay, when that UV light hits your ozone molecule, so here's 3 oxygens, see that, 3 oxygens, so the UV light comes and it hits that bond, it absorbs the energy, and then what happens, it breaks. And so you're left with an oxygen and an O2 molecule, which is called oxygen, and just a single O, which we call an oxygen radical. So the same wavelengths of UV light do not have sufficient energy to break stronger double bond of oxygen. You really need higher energy. So now you should be wondering, okay, so if all this ozone is getting broken up in the light and we're just getting oxygen, so how do we maintain that ozone layer? Wouldn't it all just disappear and become oxygen? Well, we actually have ozone reformation, and we call this the Chapman cycle. This is the overall picture, just to make your life easier at first. You have ozone plus the UV becomes O2, oxygen plus the O radical. So it happens that O2 plus the oxygen radical, they react together and they produce ozone plus heat. And so the energy absorbed is endothermic. At the end, you release energy, and that's exothermic. So notice the net is pretty much the same. You have energy going in, energy coming out. You have ozone going in, ozone coming out. So ozone is just reformed over and over again. And if you were to break this, these two reactions into multiple steps, and this is actually a very simplistic version, and the version on the right is still simplistic, but it'll give you a little bit more information. So here you have your oxygen. After it's been broken down from ozone, you have oxygen left. You have UV photons still hitting it, and it can get broken down into more O radicals. And these O radicals can react with more oxygen, okay, and these are fast reactions, and can convert into ozone, okay, and this is your fast reaction. So you're creating a lot of ozone rapidly. And your more slow reaction, you can actually take ozone to react with O radical to produce oxygen. But this is a very slow reaction, and so you're actually producing more ozone than you are oxygen. So this is your Chapman cycle, and just saying that basically you're reproducing ozone as you lose ozone. All right, so now you have a basic understanding of the ozone layer, the stratosphere, and the importance of the ozone layer to life here on Earth. In the next lecture, in the last lecture for this section, for this week, we will talk about the ozone hole. All right, I will see you soon.